Ladies and gentlemen, please take a seat. Good morning, everybody, and welcome to the 2018 Bodhi Lecture. It is my distinct pleasure to speak to you today. I do so in place of the 2017 CSS President, Dr. Edwin Chong. Ed is unable to attend today, and we send him our best regards. Today's speaker is Dr. Mark Spong. Dr. Spong received his Doctor of Science degree in System Science and Mathematics in 1981 from Washington University in St. Louis. He held faculty positions at Lehigh University, Cornell University, and the University of Illinois at Urbana-Champaign. He's currently a professor of systems engineering, electrical and computer engineering, as well as the holder of the Excellence in Education Chair at the University of Texas in Dallas. He served as dean at the Johnson School of Engineering and Computer Science at UT Dallas from 2008 until 2017, and during his tenure, he added 4 Department of Engineering, 9 new degree programs, and more than doubled the number of students and faculty. His research interests include robotics, mechatronics, and nonlinear control theory. He has authored and co-authored more than 300 technical articles, 5 books, and a patent. Dr. Spong has received a long list of awards for his distinguished research activity. I will give you just a short selection here. He is the recipient of the 2018 Bodhi Lecture Prize from IEEE CSS, the 2016 Nyquist Lecture Prize from the ASME, the 2011 Pioneer in Robotics Award from the IEEE Robotics and Automation Society, the first IROS Harashima Award for Innovative Technology in 2007, Senior Scientist Research Award from the von Humboldt Foundation, Distinguished Member Award from IEEE CSS, the Ragazzini and Hugo Schack Award from the American Automatic Control Council, and the IEEE Third Millennium Medal. Dr. Spong is a past president of IEEE CSS and a fellow of both IEEE and IFAC. The title of his presentation today is The Centrality of Control Theory in Robotics. Please join me in welcoming Dr. Spong.
Well, thank you very much, Francesco, for that kind introduction. And good morning, and I thank all of you for getting up this early and attending my talk. It's truly an honor and a pleasure for me to be here. And I want to particularly thank Ed Chong for giving me the honor of the Bodhi Lecture. I know Ed really wanted to be here, and I certainly wish him all the best in his recovery and good health. So the title of, as you see, is The Centrality of Control in Robotics. It's not going to be a typical research talk where I talk about the recent work of my students and current problems. I wanted to sort of paint a bigger picture, part history, of maybe a little philosophy, and pick one area of control that has had an impact on robotics. So there's really almost no area of control theory that has not been applied to robotics, of course, from model predictive control to optimal control, feedback linearization, backstepping, etc. So that's not what I mean by centrality necessarily. But I'm going to talk about one example of how the control community has made a contribution, namely energy shaping and passivity-based control. And I'm going to give illustrative applications in biped locomotion, gymnastic robots, and network robots, and try to show how the same theme, the same paradigm makes control design easy in these 3 applications. So the talk is definitely aimed at the non-robotics experts. We're all control experts here. But I want to talk to the people who are not necessarily doing robot control. So I'm only going to give the very simplest versions of results and obviously no proofs and things like that. But the main goal, I hope we'll have some fun with this talk. first question you might ask is there a connection with Bodie and robotics? Does Bodie have some connection to robotics? It turns out that he does, that during his work during the Second World War, and I'm quoting mostly from Wikipedia here, Bodie designed the first wireless data feedback loop in the history of automatic control systems with his development of a robot weapon. And the word robot appears 10 times on his Wikipedia page. This was an automatic anti-aircraft artillery system known as Director 7. This is shown here. This is basically took radar data and calculated the command to give to the artillery shell and it was designed to shoot down the V-1 rockets, which themselves were robot weapons. So you can think of this as perhaps the first example of robot-to-robot combat. The computer science folks talk about something they call Moravec's paradox, after Hans Moravec at CMU. And the way they state it is that low-level sensory motor control tasks require enormously more computational resources than high-level reasoning. So what does that mean? Well, the classic example of that is chess. We have chess programs that can play at the grandmaster level, but a small child can manipulate the pieces on the chessboard better than the best robot. So why is this? Well, one possible explanation is that sensory motor control has had millions of years of evolution to develop. High-level cognitive skills are much more recent from an evolutionary standpoint. Obviously, if you encounter a lion on the savannah, it's better to be a good runner than a good chess player, right? So the oldest human skills are largely unconscious, and so they appear to us to be effortless. Skills that appear effortless to us are actually among the most difficult to reverse engineer. Things like walking, running, grasping, catching, and throwing are actually quite difficult to build a robot to do these tasks. So the easy way to state Moravec's paradox is what appears easy for us is actually very hard for robots. And converse also true that some of the things that we think are hard, like figuring out chess strategy, are easier for artificial intelligence systems to do. So I'm going to focus in this talk on the sensory motor control problems, and that has applications that I mentioned, but I think this idea of this implication of Moravec's paradox has also important implications for things like autonomous vehicles and the like. So the outline of the rest of the talk is as follows. If we're going to talk about robot control, we ought to be able to define what is a robot. It turns out not to be that easy. I don't think there's a generally agreed upon definition, and I'm not going to solve that problem today necessarily. But I do want to say a few words about that. And then I'm going to talk about passivity and energy shaping and passivity-based control, which is very much related to energy shaping. And I'm going to finish with the application in networked robots, which is a very important topic these days, and give a few final thoughts if there's time. So what is a robot? The early definition in around 1980 from the Robot Institute of America defined it as a reprogrammable multifunctional manipulator, because robotics at that time was primarily dealing with factory automation and robot arms, right? So that definition is obviously no longer true or adequate. We have lots of other things we call robots, humanoids, vacuum cleaners, snakes, Mars rovers, and the like. And in fact, the term robot has become quite overused. We have robots crawling the internet, robot toasters, robot lawnmowers. You can actually go to Amazon. I found a robot cat litter box. I found a robot holster that you can clip your iPhone to your belt. So companies have figured out that rather than selling a crock pot, if they sell a robot crock pot, they increase their market share. So it's come to the point where the definition is rather meaningless in general. However, a popular definition in the robotics community is sort of the Rod Brooks definition, I would say, is a machine that transforms sensing into action, right? So the robot senses the environment, and then there's some computation, right? A computer that just interprets the sensing and gives commands to the actuator to act back on the environment to do some useful work. Well, if you go back to 2002, I think, to the workshop that was chaired by Richard Murray on future visions of control. You find the following sentence in the report that his committee wrote. It says, the basic feedback loop of sensing, computation, and actuation is the central concept in control. And so if you look at these two definitions, it's hard to distinguish the definition of a control system from the definition of a robot as a machine that transforms sensing into action. So in this sense, feedback control is the central concept in the definition of a robot. I'm going to modify this a little bit because I really like the Matt Mason's notion of a duality between manipulation and locomotion. And you can read his 2018 review of this in the annual review of control, robotics, and autonomous systems. Manipulation involves moving an object from place to place, and locomotion involves moving yourself from place to place. And he talks about a sort of a duality between these two notions. Here's an interesting example if you look at the dung beetle. So the dung beetle uses its front two legs to locomote, and its back four legs to manipulate the ball. Let me start the video. So it's sort of at the boundary between manipulation and locomotion. Which is the locomotion and which is the manipulation? Is he locomoting over the ball? Is he manipulating the ground? Something like that. So the boundary between manipulation and locomotion is maybe a little fuzzy here. But he says for each lesson learned in locomotion, we can look for a dual lesson in manipulation and vice versa. So I really like this because, in fact, in the 90s, when Brad Bishop was building the air hockey robot at Illinois, we actually recognized that this sort of a duality, that juggling, early experiment of Rizzi and Koticek, juggling involves establishing the periodic motion, which can be thought of as running gaits. Air hockey we thought of as running over irregular terrain. So let me play this video.
We have been inspired to a great extent by the work of Rizzi and Koticek, who have developed a 3-degree of freedom juggling robot. While juggling can be likened to running over level ground in the sense that both involve the establishment of stable periodic motion, air hockey can be likened to running over highly irregular and uncertain terrain where frequent gait changes are necessary and real-time vision must be used to generate suitable foot placement. Thus, robot locomotion forms an important long-term goal of our research.
So I'm going to propose a slightly modified definition, and I have no illusion that it's any better than anyone else's or that it will be universally agreed upon. But I'm going to say a robot is a machine that transforms sensing into action through feedback control, capable of manipulation or locomotion. So I use manipulation or locomotion as a necessary condition to be a robot, and I do not use the word autonomy in the definition. So that's another thing that could be discussed. The definition is broad enough to include things like autonomous cars, robot vacuum cleaners, and the like, but vague enough to lead to some interesting discussion. So if you have comments or your own definition, we'd love to hear it. Okay, so let's move a little bit into the technical portion. I'm going to talk about passivity and energy shaping. Passivity is so well known in the control community. There are books and papers galore on this topic, so I'm not going to say much other than just to set the notation. So we have essentially a system with m inputs and m outputs, u and y, and n-dimensional state vector. And of course, we say it's passive if there's a continuously differentiable, non-negative definite function that we call a storage function, scalar function from R into R, satisfying these conditions. And for the purpose of this talk, it's fine if we think of it as positive definite, and we can use storage function or Lyapunov function interchangeably. But the idea is that the derivative of the storage function is bounded by the inner product of the input and output, or equivalently, the integral equation shown here. And again, this is the simplest concept. There's many more refinements, strict passivity, output strict passivity, input, et cetera, et cetera. I'm not going to go into any of those details. But one thing that's important about this definition and this concept is that passive systems can be stabilized by output feedback. So if I set the output to be minus k times the input to be minus k times the output, then obviously we have the derivative is essentially the output squared, which is sign definite, and then asymptotic stability follows under some additional assumptions like, related to detectability. Think about Lassalle's theorem. Convergence can be to an equilibrium point or to an invariant manifold. And then there's other properties like parallel and feedback interconnections of passive systems or passive, so you can divide and conquer in that sense. So this is going to be an important idea for the applications that I'm going to show. So the takeaway message essentially is, if you find the right passivity relationship, then your control design becomes easier. You basically find the right passive output and feed it back. And we'll see that several times. So in terms of Lagrangian systems, which robot are special cases of what are called simple mechanical systems, is one where the Lagrangian is the difference of the kinetic and potential energy, Q is the configuration space, and these equations are quite well known. It's essentially Newton's second law. We have a mass times acceleration is equal to the force, and the force is an input vector tau minus the gravity force and some nonlinearities due to the complexity. And the total energy, of course, is the sum of the kinetic and potential energy. And the well-known passivity property is the derivative of the energy is equal to the inner product of the velocity and torque, which is a mechanical analog of current and voltage in a passive circuit. And if you think of a multidimensional robot arm as essentially a multi-link pendulum, then with no actuators, okay, it's going to swing like a pendulum, and the energy is going to be constant. So the only way to change the energy is to inject energy from the control input. So that's the basic idea, and it's a good beginning. We're going to start with that and exploit that property in more complicated designs and applications. Turns out Lagrange was actually first to recognize that minima of the potential energy correspond to stable equilibria of a mechanical system, because the vector here, G, is actually the gradient of the potential energy function, and it represents either gravity, elasticity, these sorts of potential forces. So the state of the art in robot control prior to the early 80s, around 1980, was essentially to linearize the dynamics, say along a trajectory, and apply linear control theory, because the dynamics of robot arms were considered to be too complex to do anything with. People would show slides that had pages and pages of equations that illustrating all the terms in a 6-degree of freedom robot. So once people started exploiting things like the passivity property of the robot dynamics, then we started to make progress. And I want to mention perhaps the earliest examples of that was this work by Professor Arimoto in Tokyo and Takegaki, which was called a new feedback method for dynamic control of manipulators. And it was based on a Hamiltonian formulation of the dynamics. And later on, Dan Koticek in '84 used the Lagrangian formulation in this paper he called Natural Motion for Robot Arms. And the significance of this work is that essentially exploited the property and did not involve any approximation, any linearization, but proved a global result with a very simple control, exploiting this passivity property. So the simplest version of potential energy shaping is actually just to choose the control input as the difference of the gradient of the difference of two potential functions. P is the potential energy, and P sub D is the desired potential energy that the designer can choose with a minimum at the desired configuration. So the closed-loop system remains a Lagrangian system, just replacing the original potential energy with the desired potential energy. And so the Takegaki-Arimoto control uses the desired potential energy as shown, which is a quadratic potential, which essentially has the desired configuration, QD, minus the actual configuration. And you can see that is kind of like a spring potential energy function. So their control becomes tau is equal to the gradient of the potential minus K times Q minus QD, which is a gradient of the P sub D. And then asymptotic stability of the equilibrium follows by including dissipation in the control. Well, we recognize that as basically a PD control with gravity compensation. So it's very simple, but the importance of this idea is, again, that it's shown to be globally asymptotically stable by exploiting the property of the dynamics without any simplifying assumptions or approximate linearization. So from those humble beginnings, a lot of work started in the 80s and continued to this day, using energy shaping and passivity, culminating with, I think, the excellent work of Romeo Ortega and Arjan van der Skaft and colleagues on this notion of IDA-PBC, which I don't have time to go through details of that, but it's based on so-called port-controlled Hamiltonian systems, and it allows shaping of both kinetic and potential energy while preserving the Lagrangian Hamiltonian structure, and it can be applied to many, many systems besides robots and has been. A related notion to that is what's called the method of controlled Lagrangians, which was started by Tony Block, Naomi Leonard, and Jerry Marsden. And rather than a Hamiltonian formulation, it uses the Lagrangian formulation, but it's essentially equivalent. And again, it allows shaping of kinetic and potential energy while preserving the Lagrangian structure of the system. Many, many applications. So rather than amplify on these ideas, I want to switch gears a little bit and talk about what are called symmetries in Lagrangian systems. And the math is a little more complicated, but I won't, I'll try to simplify it. So the basic idea is let Q be a smooth manifold and G a Lie group. And for our purposes here, if you pick the Lie group to be, think of the Lie group as just the rotation group, SO3, and Q is just a configuration space of the robot. That's all we're going to need to know. A function capital Phi, which takes an ordered pair, a group element and a configuration, and gives back a configuration, Phi sub G of Q. We call that a group action if it satisfies the usual properties of a group, and I won't list them, taking the identity element back to Q itself, etc. But suppose the Lagrangian satisfies this relationship. Once we have the group action phi sub Q defined, then there's a natural way to lift that to the tangent space and know what it does to the velocities. So suppose the Lagrangian is invariant under this group action. Well, in that case, then the Lagrange's equations will be mapped, the solutions of the equations will be mapped one-to-one from one system to the other. And such a Lagrangian is said to possess a symmetry with respect to this group action. And as a result, solution trajectories are invariant. And what I mean by invariant is they're mapped from the configuration space to the configuration space after applying the group action. So typically the kinetic energy in a Lagrangian system is invariant under rotations and translations of the inertial frame. In other words, giving rise to symmetries with respect to SO3, the rotation group, or the Euclidean group SE3. And symmetries give rise to conservation laws from what's called Noether's theorem in mechanics. And the potential energy may or may not be invariant. So potential energy control can be used either to break symmetries that exist or to create symmetries that do not exist. So symmetry breaking potentials have been used, for example, in Naomi Leonard's work on underwater vehicles. She used potential energy to break rotational symmetry to stabilize momentum, and translational symmetry to prevent drift. Most of the work has been on symmetry breaking. In contrast to that, Francesco Bullo and I introduced a notion that we called controlled symmetry, which basically says that the Lagrangian may not be invariant, but we have a control input at our disposal. So we could design a control to try to create a symmetry. So for each element G in the group, there may exist a U sub G, a control input depending on G, such that the closed loop Lagrangian equations satisfy this system. So Lagrangian equations with the control on the left is equal to the Lagrange's equations with the with the symmetry, with the group action, and we call that a controlled symmetry. So our main interest in this was for this notion of passive walking. So passive dynamic walking, it's hard not to be confused. The word passive in this context does not mean passivity the way I've been talking about. Passive means no actuators at all. So the way to understand this is with the rimless wheel. So if you roll a wheel down an inclined plane, of course, we know that it rolls with a constant acceleration. If we take a rimless wheel, then it'll roll down a plane at constant velocity because at each time one of the spokes impacts the surface, it dissipates energy. So here you have a balance between the kinetic energy that is increased because it's going downhill, trading potential or turning potential energy into kinetic energy, and then dissipating that energy, and it falls into a limit cycle type of a motion. Now, this has been a very big influence on the biped locomotion community, because you can actually build mechanisms starting from simple toys up to more complicated multi-link mechanisms that will exhibit this sort of passive behavior. So here's a great example of a 3D walker that was built by Steve Collins at Cornell, and it actually has no sensors, no actuators. It's essentially falling down the hill, trading kinetic and potential energy, and falling into a stable limit cycle. Now, that doesn't mean we don't need feedback control to make walking robots. What this means is, in this example, yes, it'll walk down a very shallow slope, but only that slope, right? It's very sensitive to the slope, and of course, it's very sensitive to the parameters, initial conditions. But we wanted to use that as a starting point to say, how could we exploit that to get sort of natural motion out of a walking robot? So what we did was to remove the sensitivity of the passive limit cycle to a particular ground slope. If you want to walk on level ground where there's no energy injected from the potential energy, or even uphill, we create a controlled symmetry with respect to the rotation group, essentially rotating the inertia frame. So the picture shows that we have the robot on the inertia frame. The controlled symmetry rotates the frame. The internal angles, the relative angles remain the same, and we want to design a control input that creates a controlled symmetry with respect to SO3, so that if we can do that, the trajectories from the passive walker will be mapped from the natural slope that the limit cycle exists to any slope that we want. It turns out that the control that does that is the potential energy shaping control. So we take the gradient of the potential energy, and then we compose the potential energy with the group action, where the group element G essentially represents the difference between the slope where the passive limit cycle exists and the slope you want. And then that potential energy shaping control gives us a controlled symmetry. Now, I'm leaving out a lot of details. The kinetic energy is already invariant. We had to show, in fact, that the impact map is invariant under the group action, because, as you know, the biped locomotion, it's really a hybrid system. We have the continuous dynamics and the discrete map because of the impacts, and I've glossed over all that. But it turns out that the impact map is also invariant, technically equivariant under the group action, and this simple passivity-based control, or simple potential energy control, creates a controlled symmetry. And this can be applied to any biped, no matter how many degrees of freedom it has, as long as you can find at least one passive limit cycle. So the idea is, now we put motors on the ankle, the knee, and the hip. This biped has been shown that there exist passive limit cycles. Tad McGeer actually built one. And so we apply the controlled symmetry. Here's walking on level ground. And the motion, just with shaping the potential energy, is a very natural motion. Okay. So why I like this is because, in fact, this comes out as the natural solution of an autonomous system. There's no trajectory generation, no trajectory tracking. We can add a torso, we can do a similar thing. So it's actually the natural motion of an autonomous differential equation or hybrid system with a very simple control. Okay, so let me move on to the passivity-based control, which is related to energy shaping, not quite exactly the same. So the previous energy shaping methods preserve the Lagrangian or Hamiltonian structure of the closed loop. So let's suppose that we want to use energy to design a storage or a Lyapunov function that's a function of the energy, but without requiring that the closed-loop system actually be Lagrangian. Well, to motivate the discussion, I'm going to consider the absolute simplest example I can, which is a simple pendulum, because we know everything there is to know about a simple pendulum. Let's suppose we have a free pendulum, so there's no actuator here, but suppose we have a force F acting on the bob at the end, and so the equations of motion are shown here. Tau is equal to the torque at the joint is L times F, and in the general case, this function, this force F on the pendulum, would be induced by the motion of the coupling of more distal links, right? But which would cause the pendulum to move. But for now, let's assume that we can choose F as a control input and see what happens. Well, we know that the total energy of a pendulum is given by the sum of the kinetic and potential energy, and we know that the trajectories of the simple pendulum are constant energy curves, right? So these are called first integrals of the motion. So for a constant E sub c, the set where the energy is equal to E sub c is the trajectory. And so almost all trajectories are periodic, except for the equilibrium at the downward and inverted equilibrium, and this so-called homoclinic orbit, which is if we identify pi and minus pi, it's on the homoclinic orbit on the cylinder, which means it connects the saddle point equilibrium to itself. It's the one non-periodic orbit. So suppose we want to use the control input F to stabilize a particular energy level. Well, people have used energy as a Lyapunov function to do this. I'm going to use the energy squared. So we take S to be 1/2 E minus EC squared, and then we just turn the crank and compute S dot. So the theta dot tau term here actually comes from E dot. That's a normal passivity property, which I said was a good beginning. But we have this other term in front of it. So if we define a new output to be the coefficient of tau, E minus EC, theta dot, of course, then we have the passivity property, not between tau and theta dot, but between tau and the new output Y. But then our paradigm just says, feedback the passive output. And if we do that, we get minus ky squared as S dot. And if you use LaSalle, you can show that almost all trajectories converge to the constant energy level E sub c. So keep that new output in mind. That'll show up in some form later on. And of course, if we choose E sub c as the energy on the homoclinic orbit, which is in fact the energy at the inverted equilibrium, the saddle point, then we see the difference between the open loop and closed loop phase portraits shown here. The equilibrium at the origin, in fact, persists, but now it's unstable, and all other trajectories converge to this homoclinic orbit. So think of this going forward, kind of to get ahead of ourselves a little bit. Think of these as kind of invariant manifolds, like zero dynamics in the dynamics of the open loop, and a target invariant dynamics in the closed loop. We'll see how that works. So, excuse me. I want to build up a couple of more complicated examples using the same idea. The first one is what we call the reaction wheel pendulum, and it's a very nice example because the dynamics are simple enough you can teach these to undergraduates, and we've built these in the lab. It's basically a simple pendulum that has a rotating mass at the end. So now it has two degrees of freedom, angle of the pendulum and the angle of the disk. It's a four-dimensional state space. And you can use the rotation of the disk to excite the motion of the pendulum. So basically, the reaction wheel pendulum can be modeled as a parallel interconnection of a simple pendulum and a double integrator, because of the torque of the disk by Newton's third law becomes an equal and opposite torque at the joint. And both the pendulum dynamics and the double integrator are passive systems from the input to the velocity, okay? So since they're individually passive, the parallel connection is passive, and we define a storage function to be, as before, the energy squared of the pendulum, difference between its energy and the energy at the inverted equilibrium, and the energy of the disk, 1/2 Q dot squared, and we do the exact same calculation. So I'll be brief. You do the same calculation, and you define a new output to be whatever is the coefficient of the input, and then you have a passivity property between the new output and the original control input. And then the idea is just define the right passive output and feed it back. And you can, again, apply LaSalle. You can show all trajectories converge to this invariant set M shown here. So again, almost all trajectories will converge to the homoclinic orbit. So if we want to balance it about the inverted pendulum from any initial condition away from the downward equilibrium, then we can converge to the homoclinic orbit, but it won't stay there, right? It'll get arbitrarily close, and then you can switch to a balanced controller. It can be an LQG or anything you want to stabilize it. So that actually works quite nicely. The other property of passivity that is very important is that if we have saturation on the input or on some signals, in this case on the input, that the same calculation goes through because the saturation function is a passive nonlinearity, first and third quadrant. Instead of U equal to minus K times the output, I take the saturation level of the output, and then I get the S dot is Y times sat Y, essentially, and it's still sign definite. And if you apply LaSalle, all conclusions remain the same. Okay, so saturation is important to model bounds on the actuator, or as Andy Thiel and many others have shown, you can intentionally introduce saturation to enforce bounds that can help to prove stability and these types of properties. So we'll do both. So here's an example of the reaction wheel pendulum in action here. Let me start this video. So here is the simple pendulum here. It's a free pendulum. At the end is a motor with an encoder and a disc. The rest is just the supporting electronics, the PWM amplifier, encoder board, DSP board, etc. And we apply this exactly this passivity-based control with saturation. This is actually in my home office in Champaign, so in case anybody's confused why there's a dog in the picture there. But let's see how it works. So the motor has very little torque. So if you apply the maximum current, it doesn't move much. So using the saturation to sort of pump up the energy is important. And in fact, because of the weak motor, it has very poor disturbance rejection properties. So if you tap it very lightly, it'll remain balanced. Tap it a little bit harder, it gives up and goes back into swing up mode and comes back. Okay, so it's a very nice controller that's based on essentially finding the right passive output and feeding it back. So the next example I want to use the same idea for is in robot gymnastics. The first example is the Acrobot, which was introduced by John Hauser and Richard Murray. Essentially, the Acrobot has it's a two-link robot with an actuator at the second joint and a free joint at the end. So we think of this as a hip torque with essentially hands and legs there, 2 degrees of freedom. And so the dynamics are the dynamics of a 2-degree freedom robot, but of course there's only a control input at the second degree of freedom, at the second link, and no independent control at the first. And John Hauser and Richard Murray showed that this system is not feedback linearizable. But in general, for these classes of under-actuated mechanical systems, we can linearize the number of degrees of freedom equal to the number of control inputs that we have. So we can actually use partial feedback linearization to linearize the Q2 dynamics, and we end up with a system like this. The first equation remains the same. We've just replaced Q2 double dot in the first equation by the outer loop control A2. So we have a linear subsystem, and we have what are called input-driven internal dynamics. And if you use, so we can use linear control to stabilize the linear subsystem, and if you do that, the zero dynamics, represented by the first equation with Q2 dot equal to 0, is actually a simple pendulum. And of course, it's non-minimum phase because its dynamics are as the open loop dynamics of the simple pendulum, periodic trajectories. So it's actually very important that we still have the control input entering into the internal dynamics, because if we want to control this non-minimum phase system, we can reintroduce coupling with the term A2, and the way we do that is exactly to add a term sat M K3 E minus EC Q1 dot, which basically represents the total energy minus the energy of the homoclinic orbit on the zero dynamics manifold. And then the trick is to find, tuning is an issue for, as you get more and more degrees of freedom, find the saturation level and the gains, so in fact that you make this manifold attractive, so in fact it will converge to the zero dynamics manifold. And when you do that, here's a simulation of just 2 degrees of freedom. So with only 2 degrees of freedom, the motion is actually, I think, surprisingly normal looking. So it swings up, and then at the top you switch to a balancing control. So a more interesting example, we can actually add a shoulder to this. So now we have 3 degrees of freedom and 2 control inputs. We have a shoulder torque and a hip torque. And so then in this case, we can linearize 2 degrees of freedom. We get a linear subsystem for the 2nd and 3rd degree of freedom. And of course, the outer loop controls drive the internal dynamics. But again, because we have under actuation degree 1, we have two-dimensional zero dynamics. And in fact, the dynamics on the zero dynamics are those of a simple pendulum. So again, it's non-minimum phase. So we do the same thing. We apply the outer loop control to stabilize the linear subsystem and re-inject coupling to the first link through this saturation of the energy function that we've been using on all these other examples. This simulation shows what's called a giant swing. So a giant swing is going to swing over the top and then balance. See how that works. So now you see it has a shoulder and it's moving. And again, it's very natural looking motion. Here comes the giant swing, wait for it. Okay, so again, what I like about this idea is that this is basic. You're seeing the solution of an autonomous differential equation. And there's no trajectory planning, there's no tracking, it just comes out of as the closed loop natural dynamics. And you could see if you saw the giant swing, the last swing, all the links were extended straight, so it was actually behaving, the control enforced the motion of a single link pendulum. So it was on the zero dynamics manifold and converged to the homoclinic orbit. So very nice, I think. So the last topic I want to talk about is passivity and network control. And I have plenty of time here, I'm going fast. So, well, as you know, a lot of people use a model of a multi-agent robot network as a single integrator. So you can model each agent as an integrator. And then the problem of things like consensus becomes largely a graph theory problem. You look at the interconnection graph and the properties of the graph to show consensus. But of course, we know that an integrator is the simplest example of a passive system, right? If I take the output y equal x and the storage function 1/2 x squared, then the derivative is x times x dot, which is y times u. Well, then the simplest consensus protocol says essentially feedback the difference of xj minus xi, which is now the output, yj minus yi, over the neighbor set of agent I. So the storage function becomes the sum of the individual storage functions. And it fits into the same paradigm, right? Just feeding back the passive output, or in this case, the difference of the passive outputs over the neighbor set of agent I. So what that suggests is that we can use more complicated models. We could have x dot equal fx plus g of xu. In fact, we can actually do this for what are called feedback passive systems, in which we're allowed to have an input transformation. Ui is equal to alpha I plus beta I times Vi, where Vi is a new control input. And we define a new output, Yi equal Hi. So if we can find the input transformation and the output transformation to and generate a passivity property between the new input and the new output, then we can use the same consensus protocol of feeding back the difference of the passive outputs. And Nikhil Chopra and Eric Rodriguez, two of my students, have used this for multi-agent coordination with more complicated dynamics, and even bilateral teleoperation, where you think of a master-slave robot as a synchronization problem, even with time delays. And so you can have quite complicated, a general Lagrangian system with the same passivity paradigm, which fits into this idea, this notion. So I want to show one example of that, which is work that we did with Professor Masayuki Fujita and his students, exploiting passivity on SO3 and SE3. So when we want to coordinate agents on SO3, essentially it's attitude synchronization. We want them to orient to the same direction. SE3, we want perhaps position and orientation coordination together, or synchronization. I'm not going to talk about that. But here, if we have a configuration, which is a position and a rotation, this is just the exponential of a twist, which is represents the rotation matrix, and the homogeneous coordinates here. If we define this function phi sub g, basically it's the norm of the position plus this term is a measure of the norm of the, in some sense, of the orientation. We can, rather than using total energy, we can kind of think of this as an energy of the position and orientation. If we, so we're going to, in this example, we're going to be using velocity inputs and not torque inputs. But if we take that function and differentiate it, turns out you come up with a function, phi dot is equal to the inner product of v and pi, where v is just linear and angular velocity. And this function, pi, is whatever comes out of the computation. And this notation, this just picks off the skew symmetric part of the rotation, and the v operator picks off the twist. But what it says is we have a passivity property between these inputs and outputs. And so our paradigm says, why don't we choose the input velocities just to feed back the difference of the passive outputs over the neighbor set. And so if you do that, in this example, I'm only interested in orientation, so I don't worry about I keep the velocities the same. But the orientation, the angular velocity input, is given by this expression summed over the neighbors of each agent, and this product of these exponentials with a minus sign here is basically the rotational analog of the difference of the orientations, right? So it's exactly the same idea, and you can show that using this as the network achieves attitude synchronization. And here's a little experiment done in Professor Fujita's laboratory with 4 agents with the nearest neighbor communication. So each robot can sense other robots in some particular radius, and then we'll see what happens. So the graph at the bottom shows the connectivity, and they synchronize their orientation. When the student puts in a virtual robot you can think of as a leader, they synchronize to that. And when he moves to the other side, you can actually see the information flow through the network as first one robot sees it, then the other sees it, then the third one sees it, and they all end up synchronizing their attitude. And when he puts it in the middle, they all see it at the same time, and so they all turn and synchronize. But again, the control is basically feeding back the difference of passive outputs. Okay, so to recap, what we've shown is how energy passivity methods result in a simple design. It essentially pushes the problem to finding the right storage function, which is like finding the right Lyapunov function that we know that can be a hard problem. But find the right storage function, define the right input-output pairs, and then when you do that, the control design actually becomes easy. You're just feeding back the passive output. And we get natural motion behavior, okay? The closed loop behavior really becomes the solution of an autonomous system. So I'm not doing any, as I said. And we still need trajectory planning in many applications, but in these applications, I find it very interesting that we get this behavior from an autonomous closed-loop system without generating trajectories or planning. So these methods are attractive for these types of sensory motor control problems: walking, gymnastic robots, multi-robot networks, and so on. Okay, so I promised some final thoughts here. So autonomy is the holy grail in robotics these days, and I didn't require autonomy as a definition of a robot. David Mendel's work, he says that autonomy connotes a broader sense of self-determination than simple feedback loops, and incorporates ideas from artificial intelligence and other disciplines. So I think that most people would agree that if we look at the work that's being done in our community, the current level of autonomy in robotics does not really represent true cognitive skills. It doesn't represent an ability to reason or make decisions beyond what the control system designer intended. So the best implementations of autonomous robots are really the result of superior modeling and feedback control, and not the results of AI. In other words, we're really not there yet where we have true cognition in AI-based robots. I want to put up this example just as not to be controversial, but to show it as an opportunity for us. There's a recent trend which goes by the name of from pixels to torques. And the idea, as I understand it, is suppose you have an autonomous vehicle with a camera, you take a raw image, feed it into a neural network, and out comes the control input. So as a control theorist, it makes me a little bit nervous, because I've seen this type of high-level output to low-level control loops show quite poor performance in things like brain-machine interfaces, controlling prosthetics, robot soccer. You know, Raffi Andrea beat the world by not doing this, but by using the vision for high-level decision-making and having very nice low-level modeling and control and planning. So rather than criticize this, I think this is an opportunity for us, and I'm very pleased to see, of course, that we have workshops on learning here. We have many sessions and papers on learning. So our community is getting into this, and I think we'll make good progress. So Pramod Kargaonkar and Munter Dali have a recent paper in the Annual Reviews in Control where they discuss the robustness issues inherent in AI systems. They don't adapt well to unforeseen changes in the environment. There's a paper shown here below that shows that you can have an arbitrarily small perturbation in a neural network system, and it can misclassify quite badly. So I see the role of control theory for our field to achieve autonomy, this holy grail of robotics, is number one, continue to do what we do best, and that's good modeling, identification, and control to improve the sensory motor control problems. After all, those are the hard problems, right? It's the walking is harder than the thinking in some sense, right? And bring control principles and best practices into AI and machine learning. So because machine learning has had success in areas like text recognition or chess, should not give us a false sense of optimism about its application in autonomous cars, brain-machine interfaces, prosthetics, or humanoid robots. Those are actually the hard problems, and we should not view it necessarily as a criticism of AI. We should view it as an opportunity to work together and use best practices and control, make it our own in this community. So with that, I want to thank many of my students, former students, co-authors, colleagues, and of course with apologies to the many who are not referenced in this talk. I've only given very brief examples of some of the simplest control ideas. And finally, special thanks to Magnus and Seth and Matt for some recent discussions in Atlanta that were very stimulating on this topic, where we essentially failed to reach consensus on what is the definition of a robot. But I think we have a long way to go in many areas, including defining robots. So thank you all for your attention. I really appreciate you coming here.
Thank you, Mark. That was fascinating and inspiring. My congratulations. Dear colleagues, as customary, we won't have a question and answer session, but do please join me in congratulating our 2018 Bodhi lecturer, Dr. Mark Spong.